All right, thank you. Yeah, so I'm going to be talking about Fidelius. This project is joint work with a small army of Stanford undergrad and master's students whose names you can see on the slide, as well as Giancarlo Pellegrino from CISPA and Dan Bonnet. So the problem that we're interested here is that all the time users are asked to put sensitive information into their web browser window. So whether you're enrolling in online banking, you're applying for a loan online, maybe you're doing your taxes or signing up for direct deposit with your employer, you're asked to put in sensitive information like a social security number, a bank account number. And if your computer happens to be compromised by malware, either in the browser or maybe the whole operating system, you're in the unfortunate situation where the malware is able to steal all of your secrets. So the question we want to answer is, can we stop malware from reading the secrets that we type into the browser window? And of course, if we're interested in a setting where potentially the whole operating system is compromised by malware, we might have to resort to hardware to solve part of our problem. And that's exactly what we're going to do here. We're going to be using trusted hardware enclaves. And if you're not familiar, a hardware enclave is a trusted component in an otherwise untrusted system. So what a hardware enclave gives you is it gives you a small area of memory that even if the entire operating system is compromised, this memory is isolated. So you can have some code in that area, you can have some data in that area, and then the execution of that code can't be interrupted or damaged can't be tampered with by the operating system. In addition, enclaves are able to prove that they're authentic enclaves to a remote host using a process called attestation. And in our project for the implementation, we used enclaves based on Intel SGX. But there's actually nothing in particular about the system I'm going to describe that relies on SGX. We could just as easily have used any other enclave. So we could have used ARM Trust Zone or AMD's SEV or any one of the number of academic proposals that are out there to provide hardware enclave functionality. So even if we have a hardware enclave, we can have some hope that maybe we can have some kind of security even if we have software compromise. But there are still a number of challenges that we need to overcome before we can leverage the hardware enclave to solve our problem of protecting user inputs to the browser. So the first problem is that what the enclave gives you is some protected memory. But what we want to do is we want to allow users to interact with browsers. And users type on keyboards and look at displays. And the enclave doesn't have access to displays and keyboards. The enclave can only communicate to this operating system that might be compromised and needs to interact with peripherals on its behalf. So we need some way to make sure that this potentially compromised operating system and browser aren't able to intercept user secrets. Second, if we want to protect web browsers today are huge pieces of software with millions and millions of lines of code. And it would be a huge engineering feat to try to take a browser and push it into the limited space of an enclave. But even if we could pull this off, we have another problem. And this is that in these millions of lines of code, browsers have lots of vulnerabilities too. And if you take a browser and put it into an enclave, the vulnerabilities will still be there. So you could end up in a situation that's actually worse than where you started, where you have a browser in an enclave. The browser is compromised by malware. And any defense mechanism you might have, like antivirus to detect and remove malware, is actually now unable to see the attacker because it's being protected by your enclave. And you've really shot yourself in the foot here. So we're going to have to be careful of this too. So with these two challenges in mind, this is where the Fidelius system comes into play. And the goal of Fidelius is to protect user keyboard inputs from a browser that's been fully compromised. So, and we can do this without having to push the browser into the enclave. So in particular, the browser stays outside of the enclave. All that goes into the enclave is this small Fidelius functionality that we've written. And we also have a Chrome extension that allows the browser and the enclave to communicate so that the browser can take advantage of the features that the enclave provides. And what our enclave allows users to do is we have support for simple HTML forms where users can type in their sensitive data. We allow JavaScript to run in the enclave to do operations on the user's data. And we provide access to local storage as well as XML HTTP requests to send that data to some remote host wherever it needs to go. Now, another important consideration if we're building a system for the web is how are developers going to interact with it. And we wanted to make sure that to use Fidelius, developers have to make minimal changes to their websites today. So to get started with Fidelius, all you need to do is to take an existing tag that you have and add this secure attribute to it. And the secure attribute indicates that whatever this tag is, whether it's a script or an input, it's going to be handled inside of the enclave and not by the rest of the browser. In addition to the tag, there needs to be a signature added to each tag that's going to be sensitive. And this is a signature that's generated by the web server and verified in the enclave. And the purpose for this is to make sure that a browser that's sitting between the server and the enclave isn't able to tamper with the contents that are supposed to be processed inside of the enclave. Finally, and perhaps most importantly, we need some way for the user to be able to interact with the enclave and take advantage of Fidelius. So we build these dongles. You can see pictures of them here. And they implement a trusted path from the enclave to the user so that any attacker in between isn't able to tamper with or read what's being sent. So I want to start by talking about this trusted path to and from the enclave. So we built these dongles out of Raspberry Pis and attached them to off-the-shelf keyboards and displays. I want to point out that Raspberry Pis were actually really, really overkill for this project. They're just good for prototyping and quick development. But in practice, we could use much weaker processors than Raspberry Pis to do this. And the reason you'll see is because what all the dongles really do is that they allow these devices to switch between trusted and untrusted modes. So when a device is in an untrusted mode, it does the exact same thing that it would do if the dongle wasn't there. So the dongles just act as pass-through devices. So if a user presses something on the keyboard, the dongle pretends to be a keyboard and sends the key press to the computer. For the display, the dongle just receives all of the HDMI output from the computer and sends it back out on its own HDMI output to the display. What gets interesting is when we switch into the trusted mode. So in the trusted mode for the keyboard, when you switch into trusted mode, the dongle begins to simulate a second device. And this second device sends a constant stream of encrypted packets into the enclave. And these packets are encrypted with a key shared between the dongle and the enclave. So, and these are sent at a constant rate because we don't want to reveal anything about the typing patterns of the user to an attacker. So if a user presses a key, the encrypted packet is going to contain whatever key the user pressed. If the user doesn't press a key, just empty packets are going to be sent. On the display side, one thing we could do is we could do the same thing that we did with the keyboard. We could just encrypt everything that needs to be displayed and then decrypt it on the dongle. But this is really taxing, both in terms of the resources of the enclave, and also it would be a lot to ask of the dongle to repeatedly decrypt the entire contents of a high-resolution display at a good refresh rate. So instead, when we move into the trusted mode, the display dongle continues to act as a pass-through device and just send everything it receives out to the display. But in addition to the regular contents of the display, we allow the enclave to send a series of encrypted overlays to the display too. And these encrypted overlays are going to contain exactly the sensitive information that a user has typed. So in this way, we don't pay for the overhead except for the minimum overhead we need to pay in order to see like the number that a user is typing on the screen. And when the dongle gets this thing, it'll decrypt it, and it'll place it in the appropriate place on the screen. So what this looks like for users is in the prototype that we built, we have these two lights. The dongles have lights on them. And when the keyboard and display move into the trusted mode, these lights turn on. So the reason that we have two lights is that whenever you're using Fidelius to interact with a secured website, the information that is sensitive on the screen will always be displayed. So the display always needs to be in trusted mode whenever you're looking at a Fidelius secured website. But it's possible that you might switch between trusted and untrusted inputs on the keyboard. Like maybe one moment you're typing in your social security number, and the other maybe you're typing in some customer support feedback. And one of these is sensitive, and the other is not. And we need to be able to switch between them so that sometimes the normal keyboard is the one that gets through the system, and other times it's the Fidelius secured keyboard. So this is why we have the two lights. In addition to this, for the trusted display, we have a little green overlay that goes across the bottom of the user screen. And this overlay indicates what remote origin the enclave has connected to, and that is exactly the only person who's allowed to see the sensitive information that you're typing. So something that was mentioned in the previous talks, and that you might be thinking right now, is in this prototype we've built, security relies on users watching security indicators. And watching security indicators is something that's been shown again and again to not be an effective way of getting users to behave. It turns out people don't really pay attention. So I want to say this is something we just built for our prototypes so that we can see that like an alert and trained user can use Fidelius properly. If we wanted to deploy Fidelius, we'd have to take advantage of all the work that the security community has done over the last few decades and build in other things like maybe secure attention sequences and other stuff that'll help users really understand what it is that they're interacting with and when it's on and when it's off. So this is an example of Fidelius in action. On the left, you can see a photograph I took of somebody typing in some sensitive credit card information on the screen. And on the right, you can see a screenshot we took from the same computer at the time the user was typing. And this is to simulate kind of the view that malware would have if it was able to take over your computer and capture everything that your computer was doing, including the output to the display. So you can see that in real life, I saw the credit card number being typed on the screen. But the malware only sees that somebody has navigated to this page, that they've clicked the credit card number field, but then the actual digits that get typed aren't visible to the attacker. And there's a video demo of this at crypto.stanford.edu/Fidelius, so you can see it kind of working live there if you're interested. I should point out at this point, there's kind of an attack that comes to mind when I describe this system to people. And this is that what's to stop a web browser from seeing that this is a website that's supposed to use Fidelius, stripping off all of the Fidelius parts, and then just doing everything itself. Like surely the browser by itself can give you interactive display as well, where you can type in your credit card number. But this is where the security indicators I talked about on the previous slide come in. So it's kind of a generic attack against any system using an enclave that the operating system can ignore the enclave and not use it. But at least in our system, if this is happening, the user can be aware because Fidelius won't turn on and you won't notice that. Yeah, so I've talked about how Fidelius is able to secure user I/O against tampering and eavesdropping. There's also protections against replay that you can read about in our paper. But once you've secured the path from the user for user I/O, Fidelius also gives this trusted JavaScript that the server has sent access to locally interact with the sensitive data. So you can have JavaScript that's running on the whole web page, and then you can also have separate JavaScript that runs only on the sensitive data. This is kind of the Fidelius JavaScript that runs in the enclave. Everything else runs in the regular JavaScript engine. And then, of course, we only allow data to be sent to the origin that's designated in the overlay, and we don't allow it to go anywhere else. There's also a few things that Fidelius does not do that we should be clear on. So Fidelius doesn't secure hardware enclaves against side channel attacks. So there's a lot of work in the last few years showing that maybe the hardware enclaves that are deployed today don't actually provide the security abstraction that we would like from an enclave. And we don't do anything to mitigate these attacks. It's kind of an orthogonal problem to be able to build better and better enclaves. What we can do for our part is that our system is designed in a way that it doesn't rely on any particular instantiation of a hardware enclave. So whenever the next best enclave comes out, we could build Fidelius for that system as well. We just used Intel SGX as kind of what was convenient and what was available on our system. Another thing that Fidelius does is Fidelius doesn't protect against dumb websites. So if we have a website that uses Fidelius and you type in your social security number, it's secured, the browser doesn't see it, and then it gets sent off to the server. And then the server decides that it wants to do something irresponsible with your data, like give it to someone else, or just send it right back to you in plain HTML. If it sends back a page that says, hey, thanks for submitting, this is your social security number. Now the browser will see this, because this plain HTML might not be secured by Fidelius. So we have to trust that once you're willing to give some server all of your secrets, that they won't do something abusive with it. I want to talk a little bit about the performance of the system as well. So we were able to implement the component of Fidelius that runs inside of an enclave in about 8,500 lines of C++ code. So this is a really big win over the millions of lines of code that a full web browser would have if we were to push it into the enclave. And this TCB, this piece that's in the enclave, is the component that you really need to audit and be careful about, because any vulnerability that exists in this code base is going to result in malware that can run inside of the enclave instead of outside of it. In terms of the latency on the display, this is the time between when you press a key and when you can see something change on the screen. It takes about 200 milliseconds from when you press the key to when you can see the change. And you can see from the chart that it kind of scales up very slowly as the size of the trusted overlays increases. I want to mention that this is not like a necessary cost. The reason that the costs are so high is that we built this out of a prototype Raspberry Pi, where we have to do a bunch of hacks to get the display to pass through from the computer to the Raspberry Pi and then back out to the display. So this chart here shows our display pipeline. And you can see these middle 3 bars, the decryption of the overlays, decoding them, and then transferring them to the screen, which are kind of the necessary parts of this operation. They run quite quickly compared to these more expensive refresh and render stages. And the refresh and render are more artifacts of how we're using the Raspberry Pis, and not something that would necessarily be there if we were to kind of implement dedicated hardware for this operation. So we'd expect the dedicated implementation to actually be much, much faster. Despite having the unoptimized refresh rate, we're still getting refresh rates that are about 3 times faster than what you'd get on the latest Kindle e-reader, which is maybe not the highest bar, but usable nonetheless. And in addition to this, we are comparable to kind of middle market smartphones, like the HTC Resound, which is a phone from a few years ago. You can see, though, that we're not quite as fast as things like the Galaxy phones and iPhones. But the system, and you can see it on the video if you go watch, it kind of moves at a speed that's usable for a person. So to wrap up, Fidelius is a system that uses trusted hardware enclaves to protect user secrets, even if the whole OS is compromised. We have support for JavaScript, HTML forms, access to local storage, and XML HTTP requests. And we have this trusted path for I/O between the user and the enclave. And this is actually something that's kind of independent of the rest of the Fidelius system. Even if you're not interested in the web browser component and you just have a project that needs to do I/O between the user and the enclave, you can still use the Fidelius trusted path even for that component. So you can read more about the system at crypto.stanford.edu/Fidelius. And all of our code is also available on GitHub. Thanks.
Hi, Mike Brossman, Department of Defense. I was just wondering if you considered replacing your hardware dongles with a hypervisor or a stand-aside VM.
Yeah, it's totally possible to implement this in other ways, and with like a separate computer too. Yeah, we were interested in this kind of the worst case scenario where everything has been compromised, and we wanted to see if there's anything we can do there. But there's a lot of different points on this trade-off curve between what you're willing to trust and what security guarantees you get. And there's a lot of other work too that you could look at that looks at different trade-offs.
Hi, I really enjoyed the display overlay. I was not expecting that, and it was very impressive. Luke Desautel from Samsung Research America. I've seen a lot of websites where, because of HTTPS providing some encryption guarantees, they'll just send the password or other form data in plain text. So I guess I have a clarification question. Even if what I'm typing is not available to the browser, does it eventually need the data to send it over to the server? If the browser looks at the network request logs and checks the form data, would it see the plain text there?
No. So part of what you're saying is that, if the server just knows, oh, it's using HTTPS and sends back the data in the clear, this is kind of the dumb website scenario that we don't protect against. But when you type your information into the browser, it goes from the keyboard dongle into the enclave. It's encrypted in the enclave, and then the TLS endpoint is actually in the enclave. So it gets encrypted in the enclave, and the outside operating system can't see what's going on inside of that packet.
OK, so the server will still get a plain text message.
The server still learns your secrets, because that's who you're trying to send it to. But everybody in between doesn't get it.
OK.
Yeah.
I guess I have a second question if there's no one else. OK. Have you looked into NLP research, looking into the actual labels of what you're about to type into? I know at some point you'd be trusting the browser, but it'd be interesting to see if it had an extra layer and it said, that's a credit card security code. I'm going to go ahead and switch you into secure state. That way, I don't have to hit a button. I could just look at it and visually confirm that I've tapped into it and it switched for me.
Yeah, absolutely. That's a great idea. So I showed that you have to add this secure attribute to a paid tag to know that it's trusted. But there's no reason why you couldn't have some other software that goes and detects when you have sensitive information. Yeah, that could totally be compatible with our system.
Cool. Thank you.
All right. While we have Stefano set up, maybe let me ask one more question. I know you kind of defined it outside of the threat model of your work, but particularly given the hardware security session that we had this morning, is it a good idea to trust on the implementation of these enclaves?
Yeah, I mean, I would say cautiously optimistic. I think that clearly there are attacks coming out all the time, but also people are working on improving the defenses. So even if today's enclaves might not quite be there yet, I think that maybe in a few years, I mean, maybe I'll have to regret this, but I think in a few years maybe we can have more confidence in enclaves.
Okay. Let's thank our speaker one more time.